All right, greeting class. It's Monday, so uh, so I hope you had a good weekend. So let's continue where we left off. So on Friday, we began chapter 15 with differentiation in several variables. So with chapters 13 and 14, um, we were exploring concepts with differentiation and a little bit of integration in three space. So we're applying concepts that we knew um, for calculus in a three space sense. So now we might extend beyond a three space. So on Friday, we introduced a couple of functions that might, have be functions of two or more variables. So an example of a function that's in two variables would be the area function that depends on x and y, where x is the base and y is the height. And then an example of a function in three variables could be the distance of a point in three space between the origin and that point P. So then that's a function of x, y, and z. Okay, so we explore some notions there. Um, Now I'm backtracking because I wanted to kind of revisit this example one. Now we did this in class. This was fine. Example one asks us to talk about the domain of these two functions. So in A, we had a function of two variables. And so, we were looking at it and we noticed it was like, hey, oh, so we're talking about domain. So we're thinking of what are our possible set of inputs. So then we see that the main function is like a square root. And so when you see square root, we're like, oh, well, we can't take the square root of a negative. So we need the radicand, or the inside part, that 9 minus x squared minus y, that has to be non-negative, or in other words, greater than or equal to 0. So we found that domain fine. We set the radicand greater than or equal to 0. Solve. We had 9 minus x squared was greater than or equal to y. So then we graph this inequality, as you see with the blue parabola there. But then we were also asked to talk about the range. And so when I first saw it, I was a little, had to pause for a second. And I didn't want to eat up too much time in class thinking about it. So I said I'd come back to it. So here's my revisit to this about range. So the range, if you're thinking about a three space in a three space context, say the XY plane, we put it flat on the ground. So the range is going to be a set of outputs. So in this example A, our outputs would, kind of be the Z axis, or in other words, what are the possible outputs that we can have? So now since the main function is square root, when we take the square root, we wouldn't be able to arrive to a negative result, right? We take the square root, then we can get a zero result. So if we were just kind of focus on just the Z axis, for instance, if we were looking at just the Z axis, and so we're kind of thinking, okay, can we get a value of can Z be equal to 0? And yeah, we could find an x and a y to make Z 0. So let me see. If we set the inside part equal to 0 and solved, so for instance, when x is 3, that's 9. 9 minus 9 is 0. So when x is 3 and y is 0, then we can make the output be 0. So we can actually find a value that'll make the z 0. And then can we make it positive? Yeah, we're taking square root, so we can find x's and y's so that the output will be positive. But then when we think, okay, well, can we make find a negative z, or a negative output? Now, since we're taking square root, the inside part has to be greater than or equal to 0, and then when we take square root, we wouldn't get a negative result. So we shouldn't be able to go into the negative z region. So that's why the range, or the set of outputs, would be 0 to infinity, with a square a square bracket on the 0 and going off to infinity. So the outputs would be from 0 to infinity. And then let's look at B really quickly as well. Now I know we have three variables, but you can kind of extend the idea in that sense. So if you want, you could almost think of it, a set of inputs as a flat. Now this is one way that some people have kind of visualized the four space. Now I might be kind of overstepping the bounds, but I think this works. So you can kind of visualize your set of inputs on a flat plane. So even though this is a three space, you can consider all our inputs in a flat plane, and then our outputs go up and down. So now our output could be, X, Y, Z, I don't know, some alpha 1 or something. But our inputs, imagine they were in a flat plane, and then we're just concerned with what are the possible values that our outputs could come. So if we're going up and down, up the z-axis and down the z, or that perpendicular axis. So let's kind of look at it. So in B, now the first restriction is that the y, we're taking a square root there. So, that's restricted to being greater than or equal to 0. And then when we do z, that's restricted to being strictly greater than 0. But x has no restriction. So if we made that square root of y, say y was 1 and z was 2. So now y being 1, we take the square root, so that goes to 1. So now we're just left with x. And then I purposely chose z to be 2 so that that second term will go away, because z is 2, 2 minus 1 is 1, log of 1 is 0, so that term is gone. So now when y is 1 and z is 2, the only thing that's left is x, and x has no restrictions. So that means our set of outputs is possible to get an output of 0, it's possible to get an output of any negative that we want, and it's possible to get any positive that we want. So we know at least for when y is 1 and z is 2, we can still take on any output that we want. So the set of outputs in that case in B would be all reals. Okay, so that was just a revisit to some ideas that we were talking about last class. And then as far as the range, I think the domain we were fine, but I needed to step back for a second. And usually this is what happens. As soon as I get out of class, I immediately figure out what it is. So that's why I stopped eating up class time thinking about this stuff, and just do the presentation afterwards. So the possible set of outputs can take on any value in that example. Okay. I think we also looked at doing vertical traces. So fixing one variable, like if we fix the x to a number, then we can find vertical traces in the YZ plane if the x is fixed, and vice versa. If we fix the y, we could find curves in the XZ plane. I think I'm saying that right. What's fixed there? X is fixed. I might have used the plane nomenclature a little bit incorrectly, but the idea is that if we have a 3-space object and we fix one of our variables, so say I fix my x, so then what plane are we in? There's y and z. I think that's correct. Yeah. So if I fix my x, then we're looking at the YZ plane, and we can choose different values of x to get different curves or different traces of our three-space object parallel to the YZ plane if we fix the x, and so on and so on. Just fixing the set of inputs. Okay. So that was what we did there. We explored some notions on that. We got those correct. Okay. Okay, and then that should bring us to today's lecture. So we'll continue with the section 15.1 with example 6.